This year's Nobel Prize in Physics is awarded to Alain Aspect, John F. Clauser and Anton Zeilinger for their experiments on entangled photons, thereby establishing a violation of Bell inequalities and pioneering quantum information science. This particular pioneering experiments and the discovery has created a lot of excitement, a lot of energy amongst the scientists across this world. It is opening up new ways of thinking the entire reality. Quantum entanglement is leading us to quantum teleportation, quantum encryption, and a lot of technological and scientific enhancement. That when we talk of Bell inequalities in terms like quantum entanglement, what do we mean about that? In this particular video, I am going to take you through an entire interesting and fascinating journey, how these three laureates came to the conclusion, how things were discovered, and what would be the implication of this Nobel Prize discovery in our daily life, how it is going to enhance our scientific and technological enhancement. My name is Shaunak and you're watching this video on Physics for Students. I welcome you to my channel. Before we jump into this bizarre and weird world of quantum mechanics and its further subtle details, I think that this is the right time that we should know about those three laureates who made this groundbreaking discovery. So it is the right time that we should get a brief idea about who they are and what are their contributions in science. As we start with the first alphabet of English A, let us start with A for Alain Aspect. Well, Alain Aspect is a French physicist noted for his experimental work on quantum entanglement. As you see on the screen, I've just given an overview about Alain Aspect and his major discoveries. In the early 1980s, while he was working on his PhD thesis, he performed the Bell test experiment and showed the most intriguing properties of quantum mechanics. Heard the wonderful short interview with Adam Smith of the Norwegian Nobel Prize Committee. I can tell you that Adam Smith's telephonic interview, if you listen to it, he is, first of all, he is an extremely humble person, number one. He served as a volunteer in the Cameroon because that is the place where he learned quantum mechanics, and if you hear his interview over telephone, he says that I am not up to the mark of Werner Heisenberg or Albert Einstein, but I am happy that I belong to their genre. So he served in Cameroon because that is the place where he learned quantum mechanics. And remember that when Adam Smith was questioning Alain Aspect, he told that, okay, let me make it a point that everybody tells that due to this discovery or this Nobel Prize award, Niels Bohr have won and Einstein have lost. That is not. It is not that somebody wins and somebody loses. Niels Bohr have won. That is one side. Einstein have also won, because if Einstein wouldn't have posed this famous question, spooky work at a distance, then the physicists wouldn't have embarked on a journey which took almost a long time in order to know what the quantum entanglement and the underlying physics of quantum mechanics is. He also told that the conclusion is yes, quantum mechanics resists all possible attacks, and he told that he was searching for a limit of quantum mechanics, and unfortunately or fortunately he could not find it, which led to this astounding discovery. Now, when he was submitting the paper to Swedish Academy for the Nobel Prize, he told that mentally I was accepting non-locality. We will see in this video what is locality and non-locality in quantum mechanics means. He said that I was mentally accepting non-locality. Of course, non-locality does not allow sending messages more than the speed of light. So Alain Aspect is the first person whom we are talking about in this journey of our discovering the quantum mechanics and what entanglement is all about. He's a very humble person, a French physicist who worked as a volunteer in Cameroon, and he tells that I am happy that I have lost and I have not been able to find out the limitations of quantum mechanics, and the quantum mechanics persist and resist all attacks. Born on 1st of December 1942, here is the person that we now meet, John Clauser. He is an American theoretical physicist, received his PhD from Columbia University, and he first showed that generalization of Bell's theorem provides severe constraints, and Clauser was also awarded the Wolf Prize in 2010. Now, in his interview again with Adam Smith over the telephone, he tells that it was one time when he was at Columbia University and he was strongly opposed to carry on the Bell's inequality experiment by Richard Feynman. And he told that he remembers that day when Richard Feynman threw him out of the class, telling that quantum mechanics has survived enough. You don't really need to do Bell's theorem again on the lab. But that is a wonderful kind of a memory. If you go to internet now, the internet is full of details of John Clauser and all the three laureates, and you will see that John Clauser has gone back to that old place where he first performed the Bell's theorem. So John Clauser, we meet the second person, American theoretical physicist who won the Wolf Prize in physics in 2010, and he was severely opposed by famous Richard Feynman not to carry on the experiment. But it is Bell who seriously persisted and insisted, I would say, to Clauser that he should carry on the experiment on the laboratory, and we all know what happened that, and we will see forward in our journey in today's video. On the 20th of May 1945, here is our third laureate, Anton Zeilinger. He was an Austrian quantum physicist. I've heard his, again a telephonic conversation with Adam Smith in the Nobel Prize over the telephone. It is only and only Anton Zeilinger's, I would say, superhuman effort. I would use again this word, superhuman effort, to ultimately what you can put the final penultimate show that the Bell's inequality theorem is being violated and quantum mechanics still persist in its own way. I spoke to Professor Daksh, the former student of the famous Stephen Hawking and Gary Gibbons, just yesterday, and he told me that I would give Anton Zeilinger only a Nobel Prize for his astounding and precise experiments. He used the instruments up to such a level which is beyond the comprehension of us. So Anton Zeilinger finally proved the he made it a kind of a absolutely foolproof evidence that Bell's inequality is being violated, and that is how we arrive in this conclusion. Prior to 1900, the entire world was going around with one single phenomena, the classical mechanics or the deterministic world. The entire laws of nature, starting from the force, motion, velocity, momentum, angular momentum, everything was sleek, clean and excellently devised by one single person, Sir Isaac Newton. Newton's laws of physics guides even today. Even up to, if you are not considering the microscopic level where quantum mechanical phenomena starts happening, or to the macro level where general theory of relativity takes place, in either way, when we see things all around us, starting from our school physics up to the advanced level, everything is being guided and neatly designed and predicted by the deterministic world, which is the classical world. Starting from how a pendulum oscillates, starting from where the ball will land when a cricketer hits it, starting from a cannonball landing to a specific destination, as well as the motion of the earth or the moon or any celestial orbit, are wonderfully guided, and I would say precisely determined by this deterministic world that is classical mechanics. Isaac Newton told that you give me the conditions of this world today, I will tell you exactly what would be tomorrow. This was the scenario before 1900, when things were, determined in a deterministic world, which was guided by the laws of nature and the good old Newton's laws of motions, gravitational constant, the laws of gravitation. Everything was going as it is, as has been devised and as we were expecting. herein comes a problem. As soon as we jump into the quantum mechanical world of the microscopic world, where things like go very small, starting from atoms to neutrons and protons and electrons, things starts to become getting bizarre. Things do not behave in the way that we do, and that is what we are going to look into in the next part of our video. Once we started looking into the microscopic world, we found that there are limitations in terms of Newton's laws of motion. It was during this time that great scientists like Albert Einstein, Max Planck, Niels Bohr, Werner Heisenberg ushered a new understanding of physics and things which happens around us. And that is a new era which is called the era of quantum mechanics. Now Newton, as I have just told that if you give the conditions how the world is now, I will give you exactly how the world would be tomorrow. Quantum mechanics tells that if you give the conditions right now how the world it is, I will give you probably what the world would be in the coming tomorrow in one way or the other. These probabilities provide the deepest and most precise understanding how the physical world unfolds in front of us. Now, as we know that Einstein was never comfortable, comfortable with this entire phenomena, and that is how when he coined the word which is called God does not play dice. Starting from Planck to Einstein to Bohr to Heisenberg and many other physicists, we are now in not a deterministic world, but in what we call is a probabilistic world. As we have noted when we just started talking about the awards of Nobel Prize of 2022, the root of the Nobel Prize or the entire phenomena is entanglement. Now, what do we mean by entanglement? Let me give you a quick example. Suppose there are two particles which are interacting with each other. It can be photon A, photon B. It can be an electron A or electron B. Right, for the sake of this video, we will just consider any two particles. Now, these two particles come close to each other and they start to interact into certain phenomena which we are not discussing right now, and they interact. Now when they interact, a subsequent measurement of one of those objects revealing one or another quality would have an instantaneous influence, an instantaneous effect on the other object regardless between the distance that they have been separated. What I am trying to tell you is that this particular particle, suppose it is a photon or an electron, behaves in a certain way. Maybe it says yes, and when they encounter and if they're separated, this separation can be very, very, very far. I am on Earth, it can be at Andromeda Galaxy, or it can be even at Alpha Centauri, right? So if I say yes, automatically the second particle strangely says no. If I say no, the second particle says yes. So exactly opposite phenomena starts taking place. Now this is what is called quantum entanglement, and this worried Einstein very, very much until the last days, till his last days. Albert Einstein tried to find out something which would either way declare or rule out those quantum mechanical effects and find out a deterministic world. Now right on your screen, I have just shown you a very, very simple example which shows that there is a spin up and a spin down. So there are two, there is one electron. So if that electron right here measures a spin up, regardless of the distance that they're being separated, automatically the second electron will have a spin down. Now it is something which you can tell as if that if this particle has got a spin up, then it is shouting to that second particle and it is telling, come on, I have got a spin down, so you have to go spin up, I have go spin down. And maybe this particle have got a spin down and it immediately shouts out and tells that particle or the electron that, come on, I have got a spin down and you have to have a spin up. Now this is actually what is meant by quantum entanglement. The phenomena is quite strange, and it shows that these two particles are instantaneously affected, instantaneously they are talking to each other. One state is being instantaneously communicated to the another. So now to understand the concept better, we need to understand one thing, that in quantum scale, reality is not until it is being measured. Now what do I mean by that? Now say for example, if I take a dice, Okay, I can show it right on your screen. Now when this dice is being thrown up, right, it has got a face 1, 2, 3, 4, 5, 6. It is being thrown up on the air. So what would be the probability? The probability of this dice would be 1, 2, 3, 4, 5 all at once. So when the dice is being thrown up, it means that it has got no meaning until it falls directly on the table or directly on the ground. Maybe it is taking a shape of 4 or 3 or 2, what? That means now when it is falling down, it is being determined. So quantum particles like this are something which are not, they are in superposition. That means it is in all shapes. Example of a dice. What we can understand that when a dice is being thrown, the existence of the dice is in all possible positions, and that is what is called quantum superposition. This is not the right video to talk much about quantum superposition, but it means that the dice exist in all possible ways, in all possible states to be precise. Same goes with photons. Photons exist in all possible states simultaneously until it is being measured. And when it is being measured, it is in an opposite state. Now, if they are talking to each other at instantaneously when the events are occurring, then it should be talking with a signal, and that signal should be more than the speed of light. That actually brings down the entire physics, because as per special theory of relativity, we know that nothing can travel faster than the speed of light. So if nothing can travel faster than the speed of light, then how are these electrons or the subatomic particles are communicating? How can that particle tell that, hey, come on, I've got to spin up, and immediately the second particle change its state and it is in opposite state, goes into spin down. Remember that all these particles are in a superposition until they are being measured. Now the problem is that this is called quantum entanglement. The problem which Albert Einstein and other physicists thought that these are separate particles. But no, quantum entanglement means that these are one single unit behaving, but they have got two parts. I know it sounds very, very weird, and it is very counterintuitive, I should say, but that is how the quantum mechanics or the quantum physics is all about. Einstein was terribly disturbed, and that is why he called this, which we are coming up in the next part of the video. Einstein called it spooky action at a distance. If you go to English Dictionary of Cambridge, you will find that spooky actually means something ghostly, or I would say something sinister, something which you are not comfortable at. Obviously, Einstein, being a person who belonged to the, I would say, the philosophy of determinism, doesn't like that this particle is communicating to that particle, and if the communication doesn't happen below the speed of light, which violates his own principle of relativity, then there should be some kind of a spooky distance, some kind of weird things that actually goes all around. And that actually is the heart of today's discussion, that how can this spooky distance experimentally measured and what would be the outcome. Here on your screen you see Niels Bohr and Albert Einstein sitting and talking, and this is called the famous Bohr-Einstein debate. The 1927 Solvay Congress in Brussels, where 29 brilliant scientists gathered to discuss the fledgling quantum theory, the disagreements between Bohr and Einstein and others, including Erwin Schrödinger and Louis de Broglie, came to head. Now, as you see that the Bohr-Einstein debate continued for quite long, and Aspect actually told that they have this particular Nobel Prize 2022 has put an end to the Einstein-Bohr debate, and it shows that Bohr was right and Einstein was wrong. But Alain Aspect tells that, please, the viewers, let us not say who has won, who has lost. Both of them have won. It would have not Einstein thrown this basic concept, spooky action at a distance, we would not have embarked into this wonderful journey which culminated to these three laureates getting the Nobel Prize. It was during this time that the famous EPR paradox came into it. Right on your paper, right on your screen, I would like to show you the famous paper which is of Albert Einstein, B. Podolsky and N. Rosen. It was around 1935. And this is the paper where Einstein told that it is not possible for quantum mechanics to predict something weird. Paradox actually laid the foundation of action at a spooky distance, which led to the quantum mechanical thoughts and further experiments. Einstein, Podolsky and Rosen tried to find out a theory and made a kind of a thought experiment which would tell that there should be something which is called a local variable or a hidden variable, I would say, which explain this weird phenomenon. That means this particle is born, already knows what would be this particle. This particle is born, also knows that what this particle would be. The question is that if these two particles really know the information is already encoded within that, then whatever way we do the experimentation, be it polarization, be it photon reflection or anything, it would definitely not create any effect because it is ingrained in their system when they are born. So here we come, so we have seen the Newton's deterministic world, we came into a probabilistic world, we came into probabilistic, now we saw the entanglement procedure, and in this entanglement procedure we see that Albert Einstein is not comfortable and he calls it a spooky action at a distance, and he says there are some hidden variables which definitely predicts this kind of a wizard, I would say weird and a bizarre behavior. Now it is during 1964 that the Irish physicist John Stuart Bell just thought that can we have a kind of an experimentation? Can we really see that whether Einstein was right, or is it some kind of a spooky distance, or is it quantum mechanics or something like that? So the Bell inequality theorem, which is the heart of this Nobel Prize of 2022, is actually something which we need to understand. So I would like to explain just in a few points what Bell's inequality theorem is all about. It is just an experiment which shows that there are no hidden variables. That means Einstein's a nightmare that there is a spooky distance, a ghostly, a sinister effect in between quantum mechanics really happens. So the Einstein spooky distance is happening, and in 1964, after this quantum mechanical experiments, there have been numerous experiments and it has proved that quantum mechanics is right. Now I don't have that time, or I would say this is not the right video to do that. Now if we take the 2 points, now let us take hidden variable at one part and let us take quantum mechanical effect on other part. I'm not going to show you the exact mathematics of Bell's theorem because that would demand a separate video. But if we consider the local hidden variables, but entangled particles, local hidden variables means what? That the entangled particles have predetermined properties which are complementary to each other. That means when this particle A is born, it already knows how the particle will behave, and both the particles are determined in some way that they will complement to each other, and that is what complementary or local hidden variable means. Now if we use the probability theory or the Bell's equation in the local hidden variables, what you will find is that Bell's inequality is being satisfied in local hidden variables. But we are not concerned with local hidden variables. We are concerned with quantum mechanics. And as soon as we apply the same rule, I'm not showing how there's a polarization of light, there's a deflection at an angle of 45 degrees, Bob measures something, Alice measures something, right? I'm not going into this detail. So when this type of measurement is done in hidden variables, which is predeterministic, or when the determining factor is being ingrained in them, Bell's inequality theorem is satisfied. But when we are using the same Bell's inequality theorem in quantum mechanics, we are finding that Bell's inequality theorem is highly violated. So I'm going to say, if I can show you, so you can see right on the screen, there is something which is called a sign function, right? So these sign function, test after test, the sign function correlation has been actually confirmed. And it has been confirmed that the particle does not behave linearly, which is supposed in Einstein's predeterministic world. Rather, they behave in a different fashion, in a probability, which Bell's inequality is being violated. This is the basic heart which we are coming, that Bell's inequality theorem, when it is applied to hidden variables, where it is linearly progressing, then definitely it satisfied that. But when it is applied to quantum mechanical effects, the deviation is sometimes up to a standard deviation of a factor of 5, sometimes a factor of 1. We're not going into these details, but yes, the deviation is there, and it shows that the quantum mechanical effect doesn't follow the linear progression of the particles, and they actually behave in a different fashion, and Bell's inequality is being violated. The question that you have right in your mind is that if Bell's inequality is being violated, then how are the particles communicating? Is it that they're communicating in the speed of light? That is a different issue. We can take it up later in a video. If you're interested, you can comment in the comment section. But most important is that that was Bell's inequality theorem. But as you understand, that a theorem will not be considered as a scientific theorem until it is being proved. Bell actually presupposed that this kind of an inequality theorem could happen, and he showed that Einstein's spooky distance exists. But who was the person who first took out Bell's inequality theorem and took it on the lab? That is what is coming up in the next part of our video. John F. Clauser, along with a graduate student called Stuart Friedman at the Lawrence Berkeley National Laboratory at the University of California, first took the Bell's theorem out in the laboratory. This is the first time that John Clauser experimented Bell's theorem on the laboratory, and it is actually during this time that I was telling that Richard Feynman discouraged Clauser from pursuing the experiment, arguing that quantum mechanics needed no further experimental proof, and he says in a funny manner that he was thrown out of the class by Richard Feynman. But it was John Stuart Bell who encouraged Clauser to see the research through, and in 1972 Clauser and Friedman succeeded in realizing Bell's experiment. Now this experiment involved not only spinning electrons, because spinning electrons have got certain limitation. It was done on polarized lights. Now polarized, as you know, it will behave in a particular direction, like the spin of the electron, which is either up or down, which ultimately cancels out to 0. Photon can take two values relative to the orientation of a filter. We know the sunglasses, how they are polarized, and one wave was to left in, photons polarized in the other. Now, there is a very funny story that Clauser was not actually very sure about what will happen, and he was eventually trying by heart that he would prove Einstein's theory to be correct. So he bet on a bet of $2 that this experiment would prove Einstein's right. But to his surprise, his results vindicated Bell's prediction over Einstein. The photon states appeared correlated in a way that precluded the hidden variable theory. So we understand from this, here on your screen, I have shown it in red. If you can read it out, we have measured the linear polarization correlation of the photons emitted in an atom to cascade of calcium. And you read the last line, our data is in agreement with quantum mechanics, violate these restrictions to high statistical accuracy, thus providing strong evidence against local hidden variable theory. It is so important. I was reading last night with one of the articles. Now it is here that this person at Berkeley Lab, Director Mike Witherill, he tells that experiment that Stuart Friedman and John Clauser did was so novel that it was completely underappreciated during that time. It was 10 years before physicists started to realize how quantum entanglement could be exploited. That was when the decisive experiments were done, leading to the new era of quantum mechanics which we are experiencing right now. The Nobel Prize is being awarded to these three great laureates. John Clauser was the first to carry out Bell's theorem out on the laboratory. The question is that, was his proof, I would say the entire proof, was it full proof or it carried any kind of a loopholes? We need to explore it in the next part of our video. It was not full proof, I would say John Clauser's evidence, but the reason behind is that the orientation of the lenses allowed a loophole, a problem. if hidden variable that coordinate or the coordinates of the photon's polarization somehow depends on the experimental positions of the light, then Einstein might be right. So I mean to say, you understand that a scientific theory requires a lot of permutation and combination, lot of different ingredients to put in until it comes out to be foolproof. So John Clauser's experiment carried a kind of a small loophole, and that has to be carried out by somebody else. And here we come to another person, Alain Aspect. Now, Alain Aspect carried out a series of what you can devilishly sophisticated experiments, right? And in 1982, in this test, the orientation of the lenses and everything are done in such a rigid and a sturdy manner that the initial lens configuration was erased and could have no influence on any secret process setting that polarization of the moment of their emission. Once more, the experiments found in favor of Bell and quantum mechanics. So first with John Clauser, then coming with Alain Aspect, the polarization light carried a small amount of a loophole, and now with Alain Aspect's sophisticated experiments, see how accurate they are. So a photon from an emitter is flying in a billionth of a second, and it tells that in that test the orientation of the lenses would randomly change. So if this one is emitted from this emitter 1 and it is flying down to the next emitter, in between also if there is some kind of a thing which causes an error, Einstein might be right. So they even change that orientation of the lens within a second, and even that they found that quantum mechanics follows. So that is why they tell that all attacks are being taken care by quantum mechanics. So here on your screen I would like to show you the original paper of Alain Aspect and Jean Dalibard, and here it shows this coincidence monitoring and the other details that timing experiment is done in this kind. And on the right hand side, if you can see here, you see the averages normalized coincidence rate as a function of the relative orientation of the polarizers indicated error. So we are done with the first proof of John F. Clauser, carried a little bit of loophole, further corrected by Alain Aspect. But again, as you know, scientific theories go on and on and on for further testing. We are not done yet. There might be again a a minuscule, minute error which would not give them a Nobel Prize, or which would again, make Einstein right. Who is the person who finally proved everything to be okay, and we are ready for the final conclusion? We are finding it in the next part of our video. Anton Zeilinger research at the University of Vienna further narrowed down to its utmost precision. In 2017, he led a team that used the colors of photons emitted from distant stars of hundreds of years ago to determine the settings of the experiment. Now here is a wonderful catch. Be it emitter, be it a photon, etc. These are deterministic of whatever the spooky distance or whatever things are happening. If we measure the photon or the photon which is emitted from a star, can you say that there is any kind of a determinism? It may be 20, 30, 50, maybe 1,000 or million light years apart. Even when we thought of starting this, even when Einstein thought of anything. So light emitting from such a huge astronomical distance should not have any kind of a flaw, any kind of a, I would say, error which might create a confusion among the physicists. So that is how Anton Zeilinger, right on your screen, you see the members of the Cosmic Bell team. Now what happened is that they pointed out a telescope out of each window, trained each telescope on a bright and conveniently located star, and before each measurement used the color of an incoming photon from each star which is being emitted. The color of these photons were decided hundreds and thousands years ago when they left the stars, which would give us therefore the measurement settings increase the chance that they were independent to the states of the photons being measured. Three great proofs, right? John Clauser with polarization of light finding a little bit of loophole, Alain Aspect rotating and changing the orientation of the angles of the polarizers, and then finally Anton Zeilinger, leaving nothing in this terrestrial world, taking it entirely to the astronomical phenomena, where the lights are being emitted from such a huge astronomical distance, would leave us no scope of error. There won't be any kind of an error which there would encounter. And obviously, if these are billion and million light years ago, we cannot say that during this time everything was deterministic, or there was I would say tremendous superhuman effort to measure, and thereby shows a violation of Bell's inequality theorem, and it survives. The quantum mechanics survives all the attacks. Finally, there might be a school of thought which would still persist with Albert Einstein. One is called superdeterminism. Now, we are not considering superdeterminism right now. Superdeterminism is something which tells that even before the Big Bang, even before anything came into play, everything was determined. What you would be, what I would be, what your behavior would be, what the protons, the electrons, entire subatomic particles, how would they behave. Now come on, that is out of the world. That is something which has got a kind of a school of thought, but we scientists and physicists, we are not considering superdeterminism. Superdeterminism is one of the way which would again prove a deterministic world, or in one way would prove something on a kind of a, it would save the non-locality version, and would say that okay, so everything is being proved, determined, each step by step. So superdeterminism is one of the way which might save Einstein's dream thought. But we are not considering superdeterminism. It is something, very weird to think that even before Big Bang, each proton and electron were determined, and there was a kind of a complementary behavior which was ingrained in them. The second part which also comes is not a very kind of a, I would say it is not, I won't say good or bad, it is not a way in which we would think. That is called the many world interpretations. Now the many world interpretations actually is an interpretation of quantum mechanics that asserts that the universal wave function is objectively real, and there is no wave function collapse. So you mean to say when this particle emits, it immediately generates a kind of a what I would say a superposition, from the superposition it generates a kind of a state, and immediately that state is being transcended into a separate kind of a world where I exist, and that is why, because we are transcended into a separate kind of a world, the next state which that subatomic particle would be is being determined. I mean to say that is something out of the world, although some of the physicists still considers the many world interpretation, but the Nobel Prize committee they didn't consider either the many worlds interpretation or the superdeterminism, and it is that which quantum mechanics survived. Finally, we come to the last part of the video. It is all about entanglement, it is all about superposition, it is all about quantum mechanics. But the question is that after this Nobel Prize being given to these three laureates, will it come to any use to us? Will it come to any kind of a practical use in our daily life? Will it improve our way of living? Will it improve any way in which we do computation, computers, or at all a cyber security? The answer is a big yes. Yes, definitely it is going to improve a lot. Here on your screen I have just shown you a few points which will done: quantum computing, teleportation, cyber security, quantum information, quantum optics, quantum computation, cryptography, and quantum metrology. These are immediately some of the things which the scientists are thinking. Remember that if one particle is emitted over here, and the other particle, as soon as it is being observed, or when it is being changed from one emitter to another, it immediately changes. So the spin up goes to spin down, and the spin down goes to spin up. What does it mean? Try to understand that we are improving cyber security. That means if I am communicating to you today, I am saying that hello Bob, how are you? And there is an eavesdropping, and somebody wants to hear what I am saying, hello Bob, how are you? And immediately that quantum entanglement changes the quantum state, and it says, hello Bob, I am coming to your home. Okay, so the cyber security, the networking using credit card, debit card, e-line, online marketing, etc. are much more secured. Hackers, I believe, won't be able to do any nuisance. Money will be secured, property will be secured. We can do much better online transaction. Millions of dollars can be spent without any problem. Now, this is one of the aspects of quantum computing, quantum teleportation. And now, Zeilinger told that it's not like a Star Trek teleportation. It is one state information being transferred to another, and there again we can reconstitute that matter. So it is not a science fiction Star Trek teleportation, but it's a kind of a thing which will still take time. This is something which will directly affect our life. Quantum entanglement will improve cybersecurity, quantum computing. Apart from that, I would like to show you a remarkable phenomena or an experiment which is done by one of the student of Alain Aspect. Here on your screen you see Pang Giovanni, born on 11th of March 1970, is a student of Zeilinger, and this is what he did. Zeilinger, he is actually launched a kind of a satellite called Messias, and which has got beamed pairs of photons to labs in China that were separated by more than 1,000 kilometers. Now, the group's measurements proved that entanglement had survived the journey. So, given a satellite, this satellite is emitting a kind of a information which is called a quantum key, and it is in China. You can imagine huge distance, and anybody who is willing to intercept the information is being lost, right? So anybody which gets destroyed of any attempt to intercept the information, this is huge, this is tremendous. So the theoretical part and the laboratory has already left, and we are already constructing satellites where two informations are being emitted, and thereby we can understand that if you're trying to intercept, we're trying to do anything problematic, it would get destroyed. Don't you think this is amazing? Don't you think that the entire quantum and the technological world is going to take a huge turnaround, and we are getting into a much more secured world where we can do transaction and many other things much more secure. This is all. I just try to make a kind of a brief video in which I can explain you the exact contribution of these three great people, Alain Aspect, John F. Clauser and Anton Zeilinger, what they actually contributed to Nobel Prize. We all read Nobel Prize, we all sometimes get confused with those terms like quantum entanglement and quantum computer processing, what it is. So this was the video in which I tried to give you a brief history, an idea, an overview how these things happen and why they won the Nobel Prize and how it is going to change immediately or through time to come our daily life. This is Shaunak signing off from Physics for Students, promising you to coming up with another more interesting video. Till then, stay tuned, do subscribe, like and put up your comments, and I will wait for your comments how the video was like. Till then, goodbye and have a nice day ahead.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.